Welcome back, everyone. India plans to prove that thorium can power reliable civilian reactors by moving from long-running laboratory work to practical pilot-scale designs that connect to real grids. In this video, we unpack how the thorium fuel cycle works, why India built a 3-stage program to reach it, and what the next 4 years may realistically deliver. We will look closely at the Advanced Heavy Water Reactor concept, the KAMINI research reactor that already runs on uranium-233, and the Prototype Fast Breeder Reactor that supplies the bridge fuel. We will also compare with programs in Europe and explain supply chain roles for firms like Larsen and Toubro and Bharat Heavy Electricals. Oh, and don't forget to subscribe now. India's Department of Atomic Energy designed a 3-stage roadmap that builds the materials needed for thorium use. Stage 1 uses pressurized heavy water reactors that run on natural uranium. These units produce electricity and also make plutonium in their fuel. Stage 2 uses fast breeder reactors that take the plutonium from Stage 1 and make more of it while also creating fresh fissile material. Stage 3 is where thorium moves to the center. In Stage 3, thorium absorbs neutrons and eventually becomes uranium-233, which can drive power reactors. The sequence reduces import needs and leverages domestic thorium reserves found in beach sands along India's coasts. The policy frame is overseen by the Atomic Energy Commission, with Nuclear Power Corporation of India Limited building and operating most plants. Thorium itself is fertile rather than fissile. The common isotope thorium-232 does not split easily. Instead, it captures a neutron to become thorium-233. That nucleus beta decays into protactinium-233, and then beta decays again into uranium-233, which is fissile and can sustain a chain reaction. This 2-step decay has timing implications for reactor design. In molten salt systems, engineers sometimes hold protactinium in a separate stream to avoid it capturing more neutrons. In solid fuel systems, the sequence is managed by geometry and burn-up planning. A practical complication is that uranium-233 often contains trace uranium-232, which produces strong gamma emissions as it decays. That feature requires remote handling and high-integrity shielding during fuel fabrication and reprocessing. India has already demonstrated the endpoint of this conversion path. At Kalpakam, researchers at the Indira Gandhi Center for Atomic Research operate a small reactor named KAMINI that uses uranium-233 fuel. The fuel was bred from thorium in heavy water reactors and then separated at reprocessing plants on the same campus. KAMINI is only tens of kilowatts of thermal power, so it is a research tool rather than a grid unit, but it shows the materials chain from thorium to power producing fissile fuel in practice. The Kalpakam site also hosts the Fast Breeder Test Reactor, which has produced data for decades, and the Prototype Fast Breeder Reactor, built by Bharatiya Nabikiya Vidyut Nigam Limited, which is the industrial bridge to Stage 3. The Advanced Heavy Water Reactor, designed by the Bhabha Atomic Research Centre, is India's flagship thorium concept for grid power. The core uses pressure tubes rather than a single large vessel, with heavy water as the moderator and light water as the coolant. Natural circulation is a central feature. Heat rises in the core and drives flow without primary pumps, which reduces moving parts and provides a passive path for heat removal during upsets. The design target is around 300 megawatts electric. The reactor sits under a gravity-driven water pool that can flood the core region if needed, and a poison injection system can rapidly shut down the chain reaction. The design philosophy aims for negative void reactivity and uses passive containment cooling to handle long-duration station events. Fuel in the Advanced Heavy Water Reactor is arranged to both generate and use uranium-233. Typical fuel assemblies combine thorium dioxide with a driver that can be plutonium or uranium-233, depending on the campaign. The structure creates seed and blanket regions. The seed contains the driver to maintain power, while the blanket contains thorium that breeds uranium-233. Because the reactor uses pressure tubes, it can refuel individual channels while at power. On-power refueling allows operators to move assemblies through the core in patterns that support both breeding and energy production. Bhabha Atomic Research Centre fuel designs seek high burn-up in thorium matrices, while keeping cladding temperatures and corrosion within limits that Indian fabrication shops can deliver repeatedly. The Prototype Fast Breeder Reactor at Kalpakam supports thorium by producing driver fuel. It is a sodium-cooled fast reactor of about 500 megawatts electric. In a fast spectrum, plutonium fissions well and also breeds additional plutonium from uranium-238 in the blankets. That material can be fabricated into driver fuel for early thorium campaigns. Bharatiya Navikiya Vidyut Nigam manages the project. Larsen and Toubro produced major nuclear-grade forgings and reactor structures for fast reactors and heavy water units, while Bharat Heavy Electricals manufactured turbine generator sets and other balance of plant systems. This mix of breeder capability and heavy industry enables India to assemble Stage 3 fuel cycles without relying on continuous imported fissile material. Fuel fabrication and materials handling are absolutely crucial to making thorium practical. The nuclear fuel complex in Hyderabad produces fuel bundles for pressurized heavy water reactors and will play roles in thorium-bearing elements once pilot lines are qualified. The Bhabha Atomic Research Center runs advanced fuel fabrication facilities that have already made plutonium-bearing mixed oxide for reactors and test pins that include thorium. While Chandnagar Industries and Godrej and Boyce have built precision components such as calandria parts, piping and valves for nuclear service. The Heavy Water Board maintains the national stock of moderator and works on deuterium production upgrades. This supply chain positions India to scale thorium bundles if pilot reactors confirm performance and maintainable fabrication yields. Reprocessing turns used fuel into new inputs for the cycle. Conventional Purex flowsheets extract plutonium and uranium from used fuel. Thorium needs a variant often called Thorex, in which thorium and uranium-233 separation is tuned, and protactinium issues are managed to improve product quality. India operates reprocessing plants at Tarapur and Kalpakam, and has pilot work specific to thorium-bearing fuels. Remote handling is mandatory because uranium-232 daughter products emit hard gamma radiation. Hot cells with thick shielding and manipulators handle cutting and dissolution. Waste streams go through vitrification to immobilize fission products in glass. In a thorium cycle, the long-lived transuranic inventory can be reduced compared with conventional uranium cycles, but the chemical steps must be proven at industrial uptime. Safety systems in the Advanced Heavy Water Reactor rely on passive physics. During a station blackout, decay heat warms the coolant, which rises to heat exchangers connected to the gravity pool. Steam condenses and returns by gravity. The core is designed for a negative void effect so that any local boiling reduces reactivity. The reactor uses a passive moderator cooling loop to carry away heat from the heavy water. Containment has passive heat removal through large surface area exchangers that vent to the atmosphere through filters. Operators can inject boron-based poisons by gravity if control rods fail. These layers are designed to tolerate long-duration external events, where active systems and off-site power are not available. The goal is a long grace period for recovery. It helps to compare India's approach with others. Danish firms such as Seaborg and Copenhagen Atomics promote compact molten salt units with factory construction and maritime deployment. In Europe, Rolls-Royce SMR focuses on compact pressurized water reactors, which are different from thorium concepts but relevant for supply chain benchmarking. Norway's Thor Energy worked on test fuel that included thorium in light water reactors. IE Spectrum has reported on molten salt efforts, and journals such as Nature Energy and Science Advances have covered materials and corrosion challenges. These programs give India useful reference points for design choices and chemistry options. How thorium fuel works inside the core can be explained step by step. Neutrons from fission hit thorium-232 in the blanket and create thorium-233. That decays to protactinium-233 over about 22 minutes. Protactinium-233 then decays to uranium-233 over about 27 days. The blanket is placed where the neutron flux is strong enough to power this chain, while keeping the newly formed uranium from being destroyed by further captures. Engineers design fuel movement plans that keep fuel in the right flux for the right time. In molten salt concepts, the protactinium can be shunted to a tank to decay away from neutrons. In a heavy water pressure tube design, planners use on-power refueling to move assemblies through the best zones. Economics depends on capacity factor fuel fabrication costs and local content. Heavy water reactors in India have achieved high capacity factors after early learning. If the Advanced Heavy Water Reactor can match that performance, levelized costs improve. On-power refueling reduces outages. Thorium dioxide is very stable and has a high melting point, which is useful in severe conditions but harder to fabricate and sinter. India offsets this with domestic ceramic expertise and by spreading fixed costs over multiple units. Bharat Heavy Electricals can deliver standard turbine islands. Larsen and Toubro and other fabricators can reuse tooling developed for heavy water programs. If pilot units validate these assumptions by 2026, site planning for the first grid-connected thorium demonstration could move forward with lower risk. Real-world case studies show that the pieces are indeed in place. The Fast Breeder Test Reactor at Kalpakam, for instance, has been providing valuable data since the 1980s. It's about 40 megawatts thermal and validates sodium technology alongside fuel behavior. Then, we have the Prototype Fast Breeder Reactor, which is about 500 megawatts electric, built by Bharatiya Navikiya Vidyut Nigam. The Nuclear Power Corporation of India Limited operates the national pressurized heavy water fleet and boasts extensive experience with on-power refueling machines. KAMINI, operating on uranium-233, supports neutron radiography for materials programs. Altogether, these examples inspire confidence that India can indeed assemble a thorium line transitioning from laboratory physics to grid megawatts, provided engineering and chemistry steps scale as planned. Now let's talk about regulatory and talent pipelines, which are just as crucial as the hardware itself. The Atomic Energy Regulatory Board is responsible for overseeing reactor licensing and safety cases. International Atomic Energy Agency peer reviews have been employed to test operating practices. The Homi Bhabha National Institute plays a vital role in training engineers and scientists who cycle through the Bhabha Atomic Research Centre, Indira Gandhi Centre for Atomic Research, and the Nuclear Power Corporation of India Limited. There have been numerous papers on thorium fuel behaviour, corrosion in hot salts, and passive safety published in peer-reviewed venues like Science Advances and Nature Energy. Industry coverage in IEE Spectrum also helps benchmark public expectations. This transparent publication allows investors and state planners to grasp what is proven, what remains experimental, and where schedule risk still exists. However, challenges remain, and they are quite specific. Handling uranium-233 requires hot cell infrastructure due to uranium-232 daughters. Thorium dioxide, being tough to sinter, can demand higher temperature processes and careful pore control. Reprocessing flow sheets for thorium are less standardized compared to those for uranium and plutonium. Waste management must consider gamma sources, which make maintenance rather time-consuming. Supply chains need to maintain precision on calandria tubes, pressure tubes, and fueling machine hardware for thousands of cycles. Public communication must clarify that thorium is not a magic fuel that bypasses safety rules. It is a path that trades some issues for others in ways that India finds appealing, given its domestic resources and industrial strengths. So, near-term expectations should be framed quite conservatively. In the next 2 to 4 years, the priority is to operate the Prototype Fast Breeder Reactor to full power and stable uptime, complete fuel qualification steps for thorium-bearing bundles, and finish licensing documents for the Advanced Heavy Water Reactor demonstration. By 2026, pilot fabrication lines could expand runs of thorium mixed oxide elements if test data supports it. Medium-term goals involve building the first grid-connected Advanced Heavy Water Reactor unit and collecting multi-cycle data on breeding and fuel movement patterns. Long-term questions include whether to add molten salt technology to the national path, how to scale reprocessing without bottlenecks, and how to integrate nuclear with industrial heat users. Now, let's place India's plan alongside more common reactor choices. Most of the world still builds light water reactors that use low-enriched uranium. Those units have mature supply chains and widespread operational experience. They do not exploit thorium, and they do not breed new fissile fuel, so they depend on mined uranium and enrichment. India's heavy water approach can run on natural uranium, produce plutonium for fast breeders, and then switch to thorium with uranium-233 as the main driver. The end vision is a closed cycle, with lower long-lived transuranics than standard uranium pathways. The trade-off is more complex chemistry and more difficult fuel handling that demands strong institutional capacity. International programs offer useful tests for design choices. The Danish companies aim at factory-made reactors and maritime deployment, which would change siting logistics. Rolls-Royce SMR focuses on heavy modularity within pressurized water technology. Norway tested thorium-bearing fuels that can inform cladding and pellet behavior. India can borrow successful elements from these programs, while keeping the core of its heavy water strategy. Researchers at universities such as MIT, ETH Zurich, and the Max Planck Institutes have published on corrosion, fuel salt behavior, and passive safety. Their findings help refine component choices and inspection plans for Indian reactors and hot cell facilities. The industrial ecosystem behind India's program includes government companies and private suppliers. Nuclear Power Corporation of India Limited operates reactors. Bhabha Atomic Research Centre designs fuel and reactor systems. Indira Gandhi Centre for Atomic Research runs fast reactors and materials programs. Bharatiya Nabikiya Vidyut Nigam builds and will operate the big breeder at Kalpakam. Nuclear Fuel Complex fabricates bundles. Larsen and Toubro builds heavy reactor hardware. Bharat Heavy Electricals delivers turbine generator sets and heat exchangers. Walchand Nagar Industries makes precision nuclear components. Godrej and Boyce supplies engineered assemblies. The Heavy Water Board maintains moderator supplies. These firms will also interact with international partners such as Thor Energy, Seaborg, Copenhagen Atomics, and Rolls-Royce SMR for benchmarking and component sourcing when useful. How might these pilots change the grid between now and 2029? If the Prototype Fast Breeder Reactor achieves strong capacity factors, driver fuel supply enables early Advanced Heavy Water Reactor campaigns. 1 or 2 pilot units could demonstrate on power refueling patterns that steadily increase the share of energy produced by uranium-233 over multiple cycles. Reprocessing lines would scale in steps to maintain product purity. If those steps work, India could add thorium cores to new sites, without losing the progress it has made in heavy water operations. Early results suggest that a thorium line could complement renewables by providing firm power, while industry still refines chemistry and fuel fabrication methods beyond the pilot phase. In summary, India's thorium pilots build on decades of stepwise work. The physics of breeding uranium-233 from thorium is well understood and already demonstrated in KAMINI. The industrial bridge through fast breeders is under construction and aims to supply driver fuel for early campaigns. The Advanced Heavy Water Reactor offers a practical way to start thorium on a grid scale using pressure tubes, heavy water moderation, light water cooling, natural circulation, passive safety features, and on power refueling to manage breeding blankets. The companies and institutions named here are the ones doing the work on the ground. If the next few years confirm stable operations and maintainable costs, the thorium path could become a real contributor to India's electricity mix. Thank you very much for watching. Please like and subscribe.